All right, well, thank you so much. Thank you so much for making here. I had to move my talk from Friday to today, so I really appreciate it. Like some of you actually made it, even despite a schedule change that happened at the very last minute. So this is a talk about quantum and classical algorithms for representation theoretic multiplicities. It is a joint work with Martin Lauroka from Los Alamos National Laboratory in the US and Greta Panova at the USC. The talk will be based on two papers. The first one is mine and Martin's, and it was about like a nice class of quantum algorithms. And then we put forward a set of conjectures that Greta Panova actually scrutinized in the other paper. And eventually we put it together and improved our results. And so the talk is a joint work. All right. So, and the high-level motivation here is a search for new quantum algorithms. As you know, like many successful quantum algorithms use Fourier transforms. So a very general form of Fourier transforms over an abelian group looks like this. So you work in a basis that is labeled by group elements, and you take a group element and you send it to some nice superposition that is weighted by the characters of your favorite abelian group. So those characters, it could be a Hadamard matrix or it could be a DFT, you name it. And for many algorithms, this is the key, procedure that seems to be enabling them. That includes, for example, Shor's algorithm. Now, what is interesting is that we also have efficient quantum algorithms for non-abelian Fourier transformations. So if I give you a non-abelian group, like the symmetry group, for example, there also exists a way of taking a group element of the group and representing that as a superposition of, say, matrix elements of the irreducible representations of your group. As I mentioned, this is very often efficient. Very often. Sometimes it is efficient, and a really nice example is the group SN. It was used in attempts at graph isomorphism and non-abelian, hidden subgroup problem, but we had a little less success applying these things. And so the set of quantum algorithms that I'll be talking about actually tries to use a transformation like this to do something interesting. The other motivation comes from our early work with Sergei Bravi, Anirban Chaudhuri, David Gossett, and Guan Yuzu. And also a follow-up paper by Christian Eckenmeyer and Satya Subramanian. So in that work, we studied those are motivated by the question of quantum approximate counting. So this is a concept of actually David and Sergei and Anirban with Pavel Bocian managed to define a new computational complexity class, quantum approximate counting, and we wanted to find a problem that would help us to actually support the definition of the class. And for that reason, we started looking at Kronecker coefficients, which is a nice problem in algebraic combinatorics that I'll explain. And we, together with Christian Eckenmeyer and Satya Subramanian, we first managed to put it in the class QMA, and then eventually they extended that and placed that problem into another computational complexity class called SharpBQP. And that turns out to be quite interesting. And in the process of doing that, we found a quantum algorithm that computed these coefficients on some restricted sets of inputs. We didn't really know if that quantum algorithm is useful, and if it's the only thing you can do that has similar structure that is actually based on, basically the QMA proof that we had in this work. And so this paper is actually about that, like it is studying whether that algorithm that we discovered here is actually useful, and if you can extend it. And the answer to the first question is yes, as you will see. And the answer to the other question is that I'm not sure, but I'll give you a set of pretty crisp conjectures, either about classical easiness or classical hardness of certain problems. that you can attempt to attack. All right, so here's the problem setup. All of this happens in a representation theory, so I have to give you a bit of a refresher about representations of finite groups. So, like a finite group is a finite set of objects together with an associative multiplication rule that takes two objects from the group and combines them into a third. It contains the identity element, such that if you multiply the identity element with any group element, you get that group element, and every group element has an inverse. Now, a unitary representation is a homomorphism from like your finite group to the set of unitary matrices. Actually, like for some of you who attended my earlier talk, like this is the same slide, but like basically, right, a unitary representation, like just takes the group and it maps it to unitary in a way that the map is homomorphic. So if you take two elements of your group and you map them individually to the matrices and you multiply those matrices, or you take the two elements of your group, you multiply them together, then you map it to like your unitary matrix, you're going to get the same result. The next thing I'll have to remind you of is the concept of subrepresentation. So if I have a representation, like that will act on some vector space, I'll call it vector space V, and then I can, like find another, representation called S that will be acting on a vector space W. And if the vector space W is a subspace of V, and for any vector in W, the action of S on the vector W, for any vector W from the subspace W, the action of your representation S on W is going to be the same as the action of R, like on vectors that live in W but inside of V, then you call S the subrepresentation of R. And then an irreducible representation is a representation that has no no non-trivial subrepresentations inside of it. The last thing I want to tell you on this slide is Maške's theorem. So that is a statement that if I give you a representation, I can always find a unitary transformation that block diagonalizes it into irreducible representations. And this is going to be absolutely crucial for this talk. So what is super important here is that, like, if you have a look here, and basically, and I really hope you can see it, but if you have a look all the way down at the bottom, I am changing my basis of the representation matrices in such a way that I end up with a direct sum where I have some identity that has a dimension that I like to call a multiplicity. I'll tell you more about it on the next slide. And like it tells me how many times does an irreducible representation labeled by, say, lambda appear. Right? So some of the errors may appear multiple times, and those multiplicities are exactly the kinds of quantities that we are looking for with this quantum algorithm. I also want to tell you about combining of irreducible representations. So if I give you two irreps, you can take their tensor product, and the tensor product itself may no longer remain an irreducible representation. You may still find a basis transformation that block diagonalizes it. Again, the other thing you can do with your irreducible representations is to take restrictions. So if I give you an irrep of group G, and that group G will have a subgroup H, I can take a restriction of my irreducible representation G down to the subgroup H by just plugging in only elements of H. Now, if I do this, it may also fail to stay irreducible. So an irreducible of G may not be an irreducible on H. And again, like, you can change your basis and it can break down into irreducibles of H. There are two things that I'll have to introduce before moving and actually telling you about the quantum algorithms. So the first thing is the concept of a Young subgroup. So a Young subgroup, I give you an integer partition of n, And then a Young subgroup over that partition is a direct product of symmetry groups with orders that are given by the entries of the partition. I hope that makes sense. And I will also just mention that the irreducible representations of the group Sn are all labeled by integer partitions. Or, like if you're familiar with the Young diagrams, like integer partitions are bijective to Young diagrams. So equivalently, they're labeled by Young diagrams. Okay, with all that, I can introduce the coefficients that we are, trying to compute with the quantum algorithm. Actually, these are the coefficients that we are going to be attacking. So the first coefficient are the Koska numbers. So Koskas tell you how many times does a trivial irreducible representation of the Young subgroup S mu appear in a restriction of the irreducible representation of Sn. I'll be calling that irreducible representation nu. And you're taking a restriction from Sn down to S mu. Right? So you take the restriction, you decompose it, and you count how many times does the trivial irreducible representation appear. The next multiplicity is the Little-Richardson coefficient. So there I take the irreducible representation of Sn. I'm going to label it nu. And I take a restriction down to SA cross SB, where A plus B add up to n. And I will have a look at the irreducible representation lambda of SA tensor the irreducible representation mu of SB inside of that restriction. Now this tensor of two irreps just so happens to be an irreducible representation of SA cross SB. So I'm still looking for an irrep of a subgroup inside of a supergroup when I take the restriction. The last coefficient that I'll talk about here is this thing called the Kronecker coefficient. It is the multiplicity of the irreducible representation lambda of Sn in the restriction of Sn cross Sn irreducible representation down to Sn. Now all these things, play pretty important roles in algebraic combinatorics, and the Kronecker coefficients are especially important in something called geometric complexity. So people do care about them, and there's a very important question whether you can express these quantities as sums of positive integers, or whether you need to have negative terms in the summations. And the reason why people care is that it has to do for example, for a Kronecker coefficient, that coefficient tells you if you take a tensor product of two irreducible representations of Sn, how does it break down? And Sn is a very discrete group, but very surprisingly, nobody knows how to write this coefficient, just as a sums of positive integers or something. And that problem is actually quite wide open, and has been open for many years. And it's interesting, and this work gives you a quantum angle on this. So now that I mentioned, what kinds of coefficients I'll be dealing with, I'll define the problem. So the problem is, if I give you mu, nu, and lambda, which are the labels for the irreducible representations that you see. For Koskas, you don't need lambda, but for the other ones, you do. And I give you these partitions in a unary, so this is for technical reasons. Then I ask you to compute the coefficient. And this problem is known to be sharply hard for the Kronecker coefficients, and it is conjectured to be sharply hard for Koska numbers and Little-Richardson coefficient. The conjecture is by Bach and Panova. And so, of course, we don't solve a sharply hard problem with a quantum algorithm, but what we do is that we compute these quantities under some restrictions on mu, nu, and lambda that turn out to be quite interesting. So this is the quantum algorithm. The quantum algorithm itself is a variation on Harrow's generalized phase estimation. So I don't know if you're familiar with generalized phase estimation, but it looks like phase estimation, except that in the control register it uses more complicated Fourier transforms. And in the target register it also uses more complicated representations. And the end result is also something a little more complicated. So the quantum and our variation on his algorithm is that in the control we are actually using a subgroup of the group that is represented in the target. Okay, I mean, like the algorithm looks like this. You work with the orthonormal basis both over the group and over the subgroup. You prepare a uniform superposition on the control, and you have a control action with a representation R on the target, and then you do a Fourier transform over the subgroup, and you make a measurement of the first label after you make the Fourier transform. So what does this mean? The Fourier transform looks like this, and basically like it moves you from the basis labeled by the group elements to a basis that is labeled by the irreducible representation, multiplicity, and the local dimension. And so here, when you make this measurement, you're only measuring the label. That if you've ever studied hidden subgroup problem, like this corresponds to like a weak, like measurement. Like a weak for a sampling, right? Okay. And so this is our main theorem. So if H, or calligraphic H, is the size of the circuit that implements this quantum Fourier transform over the subgroup H, calligraphic G is the size of a similar circuit for a group G. So H is a subgroup of G, right? And R is a size of a circuit that prepares rho of G of alpha. So this is some input state that is actually mixed. I won't tell you more about it, but it encodes some information about an irreducible representation alpha of the group G. So if you have these three numbers, then there exists a quantum algorithm, well, this one, that with the runtime calligraphic H plus calligraphic G plus calligraphic R, d alpha over d beta squared, computes the multiplicity of the irreducible representation beta of the subgroup H inside of the restriction of the irreducible representation alpha of G, restricted from G down to H. So it tells me how many times does an irreducible representation of H appear in the irreducible representation of G if I take the restriction. Now, if this, notice that the complexity of the algorithm is fully determined by the ratio of the two dimensions of the irreducible representations. Besides, like these three things, but we can assume that, like you are efficient. So you really care about your ratio of the two dimensions here. And the ratio is polynomial, like you can have a polynomial time algorithm for computing these things. And so this is exactly what we study. So I'm going to go coefficient by coefficient. I'll tell you what we found. And actually, what is the consequence of the algorithm that we just saw? So the Koska numbers, like for the Koska numbers, the quantum algorithm will compute 1 over the dimension of an irreducible representation nu times the Koska number of mu nu. And it will give you an approximation of this to 1 over Pauli additive error. Now, this means, because these numbers are integers, they are multiplicities, this means that you can compute the Koska number efficiently whenever the dimension of nu is upper bounded by polynomial. Now, is this quantum? Is okay, now my clicker broke, but I mean, here I have a quantum algorithm that looks somewhat complicated. And so here it's you instantiate a quantum algorithm with something concrete, and it gives you an answer. It solves a problem. And then you wonder, okay, well, is this something where I can expect quantum to help? And for this first problem, we actually proved that no, like yes, there is a classical simulation of this, and like there's no like quantum speedup. So this is not that interesting. Then you switch to little Richardson coefficients, which are where the algorithm gives you an approximation of the little Richardson coefficient, which is this quantity here, times the ratio of the dimensions. And again, you're going to get that approximation to 1 over poly other than error. So that means that the quantum algorithm is efficient if this ratio of dimensions of the irreducible representations is going to be upper bounded by some polynomial in n. So here n, by the way, is the order of the group that I'm working with, Sn. Now, in this case, we found no general classical algorithm that computes these coefficients, even under this restriction. However, computation of little Richardson coefficients shares many similarities with computation of Koska numbers. And it has something that algebraic combinatorists like to call a combinatorial interpretation. And so for that reason, we conjecture that there is a classical algorithm that solves this problem. We just don't know how to find it. So this is a challenge for you. Like when you leave today, and you have nothing better to do, like you can try to crack this problem and like disprove that there is a quantum advantage for this. And the most interesting problem that we solved, and actually sort of like the most interesting case of instantiating our algorithm is the Kronecker coefficient. So there you're computing the multiplicity of an irreducible representation mu inside of, like the tensor product of irreducible representations nu and lambda, both of S, or all of them of Sn. And our quantum algorithm, if you account for the cost of implementing the Fourier transforms over all these groups, runs in time that goes like n to the 4 times the ratio of the dimensions squared. Okay. Now, for these Kronecker coefficients, there is no combinatorial interpretation. So they're slightly different than the little Richardsons and Kroneckers. And so for that reason, actually, and even before telling you, sorry, I want to mention that the Kronecker coefficient is also symmetric in its arguments. And so you can order these dimensions in a favorable way always. And then you can say that, okay, well, instead of forcing this to be polynomial, I can just force one of the dimensions to be upper bounded by some polynomial, and the remaining two are just going to cancel to each other, even if they're exponential. So putting these two things together led us to conjecture that there is no polynomial time, randomized algorithm, even if you make this restriction on one of the dimensions. That turned out to be false, and we are quite lucky to be able to work with Greta Banova on this. So what Greta found is an algorithm that is classical and is polynomial time, if you fix constant to k. The runtime of that algorithm is here. It is some dk that is constant times n to the 4k squared plus 1 times the logarithm of n. So that kills, like a super polynomial speedup, like that you could otherwise conjecture, like in this region. However, what is super interesting is this. The algorithm here, the exponent goes like n to the 4k squared, while the quantum algorithm goes as, if you do the accounting, the upper bound on the quantum runtime is n to the 2k plus 4. So you can fix k, and we can tell you how to generate inputs for a fixed k, and you can get a very large polynomial speedups that you can make as large as you can by increasing k. So if you fix k to 2, the quantum algorithm runs in time O(n) to the 8, so this is impractical, but if you compare it to the quantum algorithm, the classical algorithm of Greta's, if you believe that the algorithm is indeed optimal, that algorithm runs in n to the 17. And I forgot to mention that her algorithm was already an improvement upon the previous state of the art. So when we make the conjecture, we compare it to the previously best known algorithm, and we knew that the algorithm isn't efficient in the regime where we can be efficient. So she improved that algorithm, but didn't quite manage to get to the same exponents as we do here. And this causes this widening polynomial gap to appear. Now, of course, I'll finish with a conjecture. So if you assume that Greta's algorithm is optimal, then there is a quantum speedup that is parameterized, and you can make it as large as you can in principle. But we don't know if our algorithm is optimal. It is the only algorithm that solves this problem under these constraints and does so well asymptotically. And again, like, it is a challenge for you to improve her algorithm and maybe disprove that there is a speed up of this sort. And so with that, I would like to finish, and thank you.
Thank you, sir. Questions?
Please.
So this is a pretty basic representation, but like, what are these coefficients useful for? Like, what is known to be multiplicities of these various representations?
Right. So if you're a physicist, the little Richardsons tell you how to couple angular momenta in physics. So if you like you may remember like the Bernoulli diagram, like you have two spin half particles and they couple to spin 1 or spin 0. How many times does each angular momentum value appear in this recoupling is the little Richardson coefficient.
Are little Richardson coefficients similar to Cauchy-Gordon coefficients?
They are related. Yeah, it's related. So this is one application. Then the Kronekers are a little more obscure, but I would say for Kronekers, the reason why they don't have, why I cannot think about clean application is that they are so brutally difficult to compute. That they're very difficult to compute, right? So I think like. But it's like fundamentally interesting, like what happens if you take 2 Arabs of SN, right? Like how do you, if I give you a representation of the symmetry group, like how do I chop it down to the basic building blocks, right? And this question appears there. So.
And do any of these theory relate to the branching rule? Like some of these coefficients
Oh yeah, sorry. So all of them are essentially branching rules, but like for different things, right? So the little Richardson coefficient like tells you. I mean, if by branching rule, like you mean, how do, like, angular momenta say coupled, like that's the LR coefficient. The Kronecker coefficient is the branching rule for, like Arabs of the symmetry group. Yeah.
Any more questions? Yeah, go ahead.
So I'm just trying to connect to your two talks.
Okay.
So this morning you were talking about spin chains and fermions and symmetric groups. So is there an interpretation of these coefficients from the point of view of spin chains? I mean, in particular, maybe in terms of this fermions.
There is, and I'll answer your question again in exactly the same way.
Oh.
Marcus's work and Anupam's work is exactly about it. So they give you, like a set of spin chains where all of these coefficients like naturally appear. Actually, all of them, not all of them, the Koska numbers and the little Richardsons, and something called the skew Koska numbers and skew little Richardsons. I don't think they have a spin chain where the Kronecker would naturally appear. Well, yes, I mean, that's exactly what they study. One of the really interesting things that connects the two works, right, is an open question about, like the when I asked, like here, when I was talking about a little Richardson coefficient, and I asked, like both us and Greta conjecture that there is a classical algorithm for this. We just don't know how to find it. In the other work, we don't know how to do this tensor network contraction for Littlewood Richardson coefficients, even though Marcos actually knows how to, find them as some sort of like natural amplitudes in Smith-Chains. So one of the problems we are actually working on with Marcos at the moment is to close down both of is to try to answer both of the open questions at the same time. So we currently, and this is not anywhere open, but like we do have an MPS MPO for Littlewood Richardsons, and now we are looking at the complexity of the algorithm that we have, and basically we are trying to solve this question by analyzing the tensor network contraction that we are getting there. So